Next, we're going to examine measurement. Measurement in quantum mechanics behaves quite differently to measurement in classical mechanics, and the reason for that is easiest to explain using one of our examples when we were originally discussing quantum mechanics. Here is a laser that emits photons. It's emitting a lovely stream of photons, and we happen to know that they're a wave because we can do interference with them. But if we turn down the amplitude, or we turn down the intensity of that laser until it gets so low we hear individual clicks of the photons as they arrive, then we're pretty sure that there is such a thing as a photon. And if we take this beam and we pass it through a polarizer, say a vertical polarizer like that, then we're pretty sure that if we put horizontally polarized light through that, we'll get nothing. Now classically what you get when you do this is you have a certain intensity before the polarizer, and you have a certain intensity after the polarizer, which is proportional to that intensity, but reduced by the square of the cosine of the angle between the polarization before the polarizer and the angle of the polarizer. So if this is horizontally polarized light and I put it through a vertical polarizer, I get nothing through. Conversely, if I put vertically polarized light through a vertical polarizer, it all goes through. I could put another polarizer and another, and I would keep getting all my light going through. So that's all fairly simple if you're thinking about this as a wave. So one of the ways you can think about that is you've got an electric field traveling along, and this is the electric field going up and down as it travels along. And if it's going up and down, then it can go straight through this polarizer. If it's going sideways, then it gets blocked and gets absorbed. And if it's going at some angle between straight up and straight down, so instead of being vertical or horizontal, it's actually at some angle in between, then what we do is we resolve that into its components in the horizontal and vertical directions, and then we can figure out how much electric field is going in those directions, and then we can figure out how much is passed through, because all the electric field in the correct direction passes straight through. And the intensity is proportional to electric field squared, so we go from a cos theta to a cos squared theta in our intensity. So that's how it works for a field. How does it work, however, for a photon? A photon coming through here, once it's gone through, if it goes through and it goes click, then we know that that is definitely a vertically polarized photon. How do we know that? We know that because if we put another vertically polarized polarizer in between, then it will definitely go through and definitely go through and definitely go through again. So we happen to know that the things on this side are definitely vertically polarized. Every single photon in there is vertically polarized. However, it wasn't necessarily true that all the photons on this side were vertically polarized. For example, we might have lost some as it gone through. And you could think of that perhaps as there were some horizontal and some vertical, and then the horizontal ones were thrown away and we're just left with the vertical ones. However, there's something particularly special about horizontal and vertical, those two directions. If we had something in between, a 45-degree angle, then we might have had all of those go through, because then we would have regarded this light as being the same kind of angle. And it turns out that in order to describe photons going through here and to get all the rules of these intensities correct, what you have to do is you have to have the polarization discontinuously change from here to here. So if I've got a vertically polarized photon, and let's build this as an experiment. So all the photons in here must be vertically polarized, and therefore this angle theta is going to determine exactly how much the intensity we get through there. But when I'm talking about a single photon going through, I'm absolutely sure that any photon in here was vertically polarized. So any photon through here was vertically polarized, and it must be polarized like this, because if I then have a whole series of further polarizers of this angle, then it would have to go through those as well. So the photon polarization here must be that angle theta. So we have a very obvious discontinuous jump in the state of the photon between the two polarizers. Here it is vertical, here it is at angle theta, so it must be, when this measurement is done, it must be doing a sudden jump. Similarly, if you have a trapping potential that has sort of two areas where you could trap something very easily, and I have some wave function here, so now I'm talking about a wave function, everyone's favorite quantum state, and it's an equal superposition of being in the two places, in the left well and the right well. If I make a measurement of this, that's going to go to one or the other. Before we make the measurement, we know it's going to go equally between these two. Afterwards, it'll be one or the other, and we don't know which. And again, that's a discontinuous change in the wave function. So how does the measurement postulate work in quantum mechanics? How do you extract measurement information from the state? Well, in quantum mechanics, each measurement is related to a specific operator called an observable. And this observable is its own Hermitian conjugate. Operators that are their own Hermitian conjugate are called Hermitian. We can tell a lot of things about observables because they're Hermitian operators. The first thing I want you to do is show that all the eigenvalues of an observable are real.